Word up. Nationwide hated. Nickel plate.
Sequel or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
Hi guys, let's get started. Yes, I'm from the hospital, but this talk is so important. This is why I'm here, to hear Benjamin Naecker talk about the query language that they built at Oxide, which is not a database company, it's a hardware company. So Benjamin has a PhD from Stanford in computational neuroscience, yet his day-to-day job is a software engineer at Oxide. So as always, if you have any questions for Benjamin while he's giving a talk, please interrupt and ask a question at any time. And feel free to do this whenever you want. That way, Benjamin's not talking to himself for an hour on Zoom. So Benjamin, thank you so much for being here. This is a big deal.
Thank you. I appreciate it. Thanks for the intro, and to you, obviously for making such an effort to be here, and to the whole database group at Carnegie Mellon. I'm very happy to talk a little bit about this DSL that we've written at Oxide. So what I'm going to do is spend most of the time actually on the motivation, basically why we ended up doing this, because I think it is a pretty unusual thing. There's a lot of reasons to not do what we're doing. And so I'm not going to dive, in contrast to some of the talks that came before me in the seminar series, I'm not going to dive too much into the technical details of the language itself. I think some of it is interesting and I'm happy to take questions about it. But it's really not the part that I think is the most valuable, that's the most transferable from what we're doing at Oxide to other folks. I think the part that's really valuable to all of you guys listening is basically, why did we do this, right? How did we go from SQL or death to some other afterlife in the form of this DSL that we've built called OxQL? So, just a little bit, I want to start with kind of like motivating, Oxide as a whole, which I think is a bit unique. So let's say you are at Big Co and you run a bunch of servers, and by a bunch, I mean like 100,000, right? So you have internal customers, different business units in your organization, you're making widgets, and you give them VMs and other sort of virtual resources, but you need to host all of those on actual servers. And so if you want to do this today, you basically have two choices. You can rent all of that from the cloud, or you can build it yourself. And there's a lot of trade-offs between these two. These are really extreme ends of the design space. So on the cloud side, you get this nice, convenient API. You can kind of interact with it through web interface and lots of different languages. It's very, very convenient. There's a ton of managed products. I mean, AWS, as an example, has literally hundreds of different things. You've got several different kinds of databases, several different notification services, obviously virtual machines as well, but tons of other things that are really, really just sort of well built and kind of just work. And you could really build any application out of all of these building blocks that they have. It's really convenient. I think the biggest selling point that we're all aware of is you basically get infinite scale immediately, right? So, I don't think I've ever heard of anybody trying to deploy a VM on something like Google Cloud and them saying, sorry, we don't have a machine to host that for you, right? It just doesn't happen. They never run out of space, basically. And the hardware is all managed for you. You just get updates to things like the host operating system, or you get new chips, new accelerators or whatever, just sort of come online for you. You don't have to worry about any of that stuff, right? If a disk drive dies, it's not your job to replace it. So these are all really, really valuable, I think, pros in the cloud model. The downside is that it's quite expensive. So especially for people who have fixed workloads, right? So if you use that infinite scale that goes up and down, very bursty workloads, it's great, right? Because you don't pay for it when you don't use it. But if you have a fixed workload, it can be very, very expensive, anywhere from 30% upwards to 300% more expensive than just sort of owning your own infrastructure and running it yourself. So as you get to that big scale of 100,000 virtual machines or something, it's pretty expensive. You give up a lot of control and ownership. You don't get to decide what hardware is run, and you may care about that, right? Or you may care about being at a capital expense, not an operating expense in your business. And so you don't get to make that choice. There may be legal or compliance issues. So we talked in the pre-meeting little huddle, we talked about, like, if you're a fintech company, right? If your Big Co makes widgets, it's fine. But if you store a bunch of credit card data, like, you may not want to be able to store the data in the cloud, or may not be legally allowed to store the data in the cloud. There are also these data movement issues. So for example, on Amazon's S3, their object storage, it's free to put data in, but you pay through the nose to take it out. And so this encourages you to put all of your computing into the cloud, use all of their services. And if you don't do that, you have either huge costs or you have huge latency issues. So there's lots of downsides for the cloud model as well. Now on the build it yourself side, the big benefit is you get to build exactly what you want. You own the hardware, you get to take the depreciation, it's a capital expense, like all of these, beneficial reasons. It is generally cheaper for fixed size workloads. It depends on exactly what you're doing, but it's overall very, very cheaper, and it sort of gets cheaper faster as you go to bigger workloads too. The downside is the biggest upside, which is that you have to own the hardware, right? Which basically means you need a place to put it. You need cooling, you need power, you need all of these different things, right? It's an administrative headache. If a disk drive dies, you have to figure out, well, which one is it? What part is it? How do I replace it? How do I source that? How do I keep track of my inventory? It kind of sucks in that sense. You have a patchwork of vendor support, right? If you buy a switch from some company and a server from another, if you're trying to talk between these two and the packet sort of gets lost between them, you're going to be really quickly in that like Spider-Man meme of them pointing fingers at each other where they both basically just blame the other vendor, right? Like it's going to be like, it's not my problem, it's your problem. And then also the management software is extra, which is annoying. You have to pay for that. You got to manage that. So it's sort of another layer, whereas the software is all that you have on the cloud, right? So if you look inside the machines that back all of this stuff, they actually look very different. So it's easier to start with the build it yourself model where we just have more experience and more data. And what you see is something like this. It's a sort of pizza box stack style thing where if you open up the hood and look inside, it's basically the same thing that we've had since I was a kid. There's a CPU, some DIMMs, bunch of fans. There's like an AC power supply. There's an RJ45. There's a VGA adapter in the back. There's sort of all of this like cruft that's come along for the ride in the last like 30 or 40 years that's still there. So those are the servers, but you also need to buy a switch, and then you need some kind of like VM management ware of some kind, which I don't know what you would use for that, but I hear it's quite expensive as companies get acquired by other companies that they kind of up the prices dramatically, or so I hear. So you have to kind of put all these things together yourself. And it's sort of a subpar product in a lot of ways, and it's complex. We actually don't really know what the machines inside, say, Amazon's data centers look like, because that's sort of their secret sauce. The closest that we actually can get is looking at something called the Open Compute Project, which is a thing that came out of Facebook's redesign of their data centers in around 2010 or so. They made a bunch of these reference designs open to try to advance the state of computing hardware. And they look something like this. So this is the Tioga Pass server, which is one part of the Open Compute Project, or OCP reference designs. But you can see it looks totally different. Different form factor, totally different size. The green part is this airflow shroud. So it's not just like a bunch of tiny little fans spinning at 8 million RPMs. It's a very different cooling design. The power works totally differently. There's no AC power supply on this thing. You power the rack, not the server. There's no VGA adapter. The only way you can talk to this thing is over the network. So it's just a fundamentally different hardware model. So if all of the big cloud providers build servers that look like this, how come you can't buy them? And this is basically where Oxide comes in. We are the cloud you own. We fill this niche, right? You buy the whole rack at a time, or ideally many racks at a time. We put all 32 servers, 2 switches, 2 power shelves in there. They're all designed to work together. We built the whole thing. So it's this vertically integrated cloud compute. You come to one vendor for support. If the switch is giving you problems, we're the vendor. If the server is giving you problems, we're also the vendor. This really gives us the ability to do lots of things that have only been available in the past to those hyperscalers. So this includes things like smarter resource management. We know exactly how many resources there are, how much overhead there is for our systems, for the virtual machines, so we can sort of place things a little bit better. Same thing for fault management. When things go wrong, we know exactly what context that's in, whether it's something that can be repaired automatically or we need to generate an alert for an operator. Because we want to give the cloud experience, everything is driven through an API, which is all public and open. So we use the API, customers use the API. There's no sort of hidden interfaces. There's obviously the power efficiency, which I mentioned a little bit about. There's no power supplies on the sleds. They're powered by the backplane, which is really great. And then, of course, for the purposes of today's talk, we have this very holistic and kind of comprehensive telemetry system as well. So speaking of telemetry, what kinds of data do we get? I think it's important to understand a little bit what the data looks like. So we have information from hardware sensors, temperature and voltage, current, fan speeds, all these different things. We get lots of networking data. almost like a huge fraction of the work is just computers talking to each other, sending data back and forth. So we get all the information about packets and bytes, both on the physical network, but also the virtual network that customers use. We get information about, say, fiber optic bit error rates or forward error correction problems. Lots and lots of information comes from the networking subsystems. We were talking a little bit about this earlier, but we have the host OS under our control as well. So we get all of this information about memory and file system usage, lock contention, that sort of stuff. We've also built the whole control plane. So we get lots of information about how that software is working. It's sort of really a whole suite of software. Just as an example, we have a distributed database for our kind of consistent data, not the time series data, but for our consistent data. And we keep track of things like transactions. How many statements are in a transaction? How long do they take? Is there contention? That sort of stuff. We monitor the API for problems like, degrading latencies, that sort of thing.
Seems you guys were using CockroachDB.
That's right.
Okay.
Yeah. So Cockroach is the control plane database, or the consistent, data store for customer data, for things like which VMs are deployed where, what hardware exists in the rack, that sort of stuff.
Got it. Awesome. Thanks.
Yeah. So where was I? Okay, so the virtual resources is another big thing. We keep track of all the stuff that the customer is using, things like virtual disk, IOs, vCPUs. The vCPU thing is going to become a pretty kind of key example. We'll use that in a few of the motivating examples coming up next. So the point that I want to make by this is just how heterogeneous the data is. We have things like gauges, temperature. So these are instantaneous measurements, temperature, voltage, current, that sort of thing. We also have a lot of cumulative counters. So there's a start time and some, monotonically increasing counter over a time window. The other thing is histograms are really, really, really important for us. So I'll get a little bit into why they're so critical. But for example, for like the virtual disk IO, I don't really care about the latency of all like read operations, because who cares if it's slower to read more data, right? What I actually care about is breaking it out by size. So we do something like bin by power of 2 sizes for all different types of operations. So I'll talk a little bit about that. And I think histograms are one of the main, are a very important motivating factor, I should say. But this vCPU data will become our primary example for a lot of the motivation. So this is like the obvious first question that people ask. You've got all this data. That's awesome. How do I query it? Right. And this, as any Joe on the internet will tell you, like it's, any kind of person would point out like, hey, it's not 2010, man, we should use SQL. And that's exactly right. You don't have to be Andy to come up with this. Like, this is where we started, right? We were like, we should use SQL because there's a lot of good reasons for doing that, right? So what are some of those? For example, familiarity, right? Every software engineer who's worked in this kind of environment has at least passing familiarity with SQL. And most people have better than that, right? It's easy enough to read. There's so many examples and documentation out there that people are basically at least, reasonably familiar with it. There's a ton of documentation for SQL, right? I mean, like books, tutorials, videos, YouTube videos. I mean, there's just stuff all over the place. There are so many examples. I was actually very curious. So a few weeks ago, I went onto Stack Overflow and looked at tags by, how common they are. There's little over 670,000 questions on Stack Overflow with the SQL tag. To give you some context, that's the 12th most common tag overall of any kind. So it's more common than like the C programming language. There's only a few programming languages that are more common, and it's things like Java or JavaScript or, Python, stuff like that. So it's extremely common. There are so many questions. You can always go to Stack Overflow for questions. So it's really, really helpful to have all of that. It's a very flexible data model, right? I mean, part of the benefit of something like SQL is that, in theory, you have this declarative syntax for saying what you want, not how to go get it. I think that breaks down a little bit in some cases. Like that's why we have the explain output, and we look at query plans and stuff like that, because I think it's a idealistic way of looking at it, but there's a lot of truth to it, right? I think there's a lot of value to thinking about it like that. And then, we are implementing this query system, right? So we can take advantage of all the tooling around a standard like SQL. So as we can use off-the-shelf parsers, and we can use a query planner and a query optimizer, even things like syntax highlighting, like all of this stuff could be very useful, not necessarily will be, but could be very useful to us if we're starting off the shelf or starting with a like SQL-like language, right? I mean, we could use a lot of this. So we took this very seriously. We said, okay, well, like SQL, please, like let's try to make that work. So we basically took that and tried to run with it. So I want to go through a few of the examples that we actually tried to do using SQL. So I built a prototype sort of front end to our database that stores the actual data using SQL. And we tried to make some things work. So one very common one that we do is just graphing vCPU usage. This is like how, customer deploys a VM, how busy is it, right? Do I need more of them? Do I need fewer of them? What does it look like? So we show folks this data in our web console, and it looks something like this. So there's just a graph over time of the vCPU usage. So that's time on the y-axis and usage as a percentage on the time on the x-axis, usage as a percentage on the y-axis. And this is in one particular state, the idling state, but we care about others, like is it running, is it waiting for IO, all of those sorts of things. So we track all of these separately. And for the most part, we let customers just pick the time range that they want, and we want to average it into something useful, like let's say 5-minute time buckets. Okay, so if we're going to do this with SQL, what might it actually look like? The first thing we need to know is what is the data format, right? So we store data that looks something like this today. This is kind of a simplified view, but basically we have a table, vCPU usage. We've got in red these kind of metadata columns, things like the ID of the VM instance that's reporting the data, the serial number of the server hosting it, the state, the CPU ID, and then on the yellow columns, we have the actual data points, right? Timestamp and vCPU usage. So if this is our data, the query might look something like this, right? Using just standard SQL, right? So I'm just selecting the data that I want. And the kind of interesting part is in those last two columns in the select clause. And we've got basically the average vCPU usage. Makes sense? This floor extract thing is doing a conversion, basically rounding down to the nearest 300 seconds. Not crazy, but this isn't that, this is sort of like, I'd say, advanced beginner SQL, right? Like it's pretty simple, but not trivial, not the first thing you learn, but pretty easy, right? The most annoying part here is the conversion to seconds when you have to do this rounding. Some database engines might support extracting other parts of the timestamp, like minute or something like that. So it's a little bit annoying that you have to do that. If you're talking about generating this in like the web console where it's a programmatic context, you could imagine just like emitting this SQL and we're just filling in that timestamp or that division, that factor, right? Based on some input from the user. So interactive usage, it might not be that great, but programmatic usage, fine, right? Except, yeah, do you have a question, Andy?
Yeah, I think it's worth mentioning, you guys are using ClickHouse to store all this data in the back end, right?
That's right. I haven't talked about that yet, but that's right.
Okay.
I'm not going to get a lot into that. I'm happy to talk about it towards the end. I have like some, hidden slides and stuff if we want to get into it. But yes, that's right. We are using ClickHouse under the hood to store all the data. So this seems like fairly straightforward, right? It's sort of tolerable, I would say, for most people, even those that are not super familiar with SQL. Except there's a problem, which is that I have lied to you about the schema that we actually have. So the data for the vCPU usage, for a bunch of technical reasons, is actually cumulative. It's one of those cumulative counters that I mentioned. So we need to, we cannot do something like average vCPU usage across all of the groups because rows are not independent from one another. If I look at later timestamped data, it includes the counters from before, right? So if I do something like average it, I'm double counting, I'm more heavily weighting data at the beginning than I am at the end. So in order to correct for that, I need to make all of the rows, all of the tuples independent. The way you would do that is with an adjacent difference operation, a successive difference operation, right? So in standard SQL, if we have the table from before, that might look something like this. And like, that's hard to read. I see people like getting close to the screen and shit. Like this is pretty bad. It's not horrible once you get into it, but like I've already lost probably half my audience because there's a CTE. I have to use this lag window function. So I'm computing, I'm already doing some partitioning of the data. It all makes sense. Like I think it's, if you dig into the details, what we're basically doing is partitioning the data by those metadata columns, ordering by timestamp within that. The lag function gives us the previous row, and I subtract the current row from the previous row, and then that gives me this difference, right? And the coalesce is there, by the way, because at the first row, there is no previous row, so you have to handle nulls there. So it all, I think, makes sense. But especially for interactive usage, like doing something like this is pretty cumbersome, I would say, for a lot of the kinds of things we want to do, where be able to have a query system that I can just walk up to and run queries like this that are sort of ad hoc. This is basically a non-starter for us. So, I think this is kind of the first example where you're kind of like, okay, maybe it's more painful than we're willing to bear at the moment. The other thing is that actually I've still sort of lied to you a little bit about the schema, or at least hidden a detail, which is that the timestamps are cumulative. And I mentioned there's some technical reasons for that. One of them is that technically our hypervisor can panic. So if the hypervisor panics, it obviously aborts the process. It takes out the VM with it. Okay, our software will restart the hypervisor, which will restart the VM. It'll sort of come back online, but now it's reporting data having a new start time, and that counter has reset to 0, right? So rather than try to handle that on the hypervisor, where it's tricky, we don't necessarily want to maintain all of that state there. What we do is continue to just report the data, and we say we'll correct for that in our query system at the end, or some system at the end. But in order to do that, what you have to do is you basically have sort of any number of monotonically increasing regimes, right, where the data has reset to 0 at some point. So to correctly deal with that, what you have to do is find all of those regimes and then add up, kind of offset the later ones by by the last value in all of the other regimes, right? So you have to kind of and you have to do that, by the way, if you only care about data at the end, you still have to do that for any restarts that are at the beginning, right? So it's very tricky to do. I'm actually not sure how you would write that in SQL. I didn't really bother trying, but it's presumably going to need some other type of windowing function. And then you also need to compute the successive differences on top of that, right? So it's very complicated, I would say.
Why are these counters cumulative, right? Why isn't it just like at this time for this some window range, this is the value that I got, versus
the main reason is that because the system, well, one of the big reasons, the system is distributed, so we can lose samples along the way, and I want to be able to correctly assess if you don't do that, if you only report sort of an instantaneous or a short time period of the measurements, you will have all of the later values missing that piece of data. Whereas if I drop a sample, the later values will now account for that. And so if there's sort of network weather on the rack, I can get some of the data later as well. And it'll still be correct, right? I still have to deal with this fact that there's this missing sample at some point in the query system, but I haven't lost data. I'm not incorrect, right? That's the main reason. But believe me, we debated this. It makes the query system much more complicated, right? Like it makes the rows are not independent, which sucks in a lot of ways. So that, kind of breaks in the SQL model, where like I have a bunch of tuples and who cares what the order is? It's no longer really true, right? And I'll get into that actually in a little bit. So this is one of the kinds of examples that we tried to make work and was pretty painful. There's another one, which is that we often, especially early in the product, we were just debugging stuff. We'd walk up to a system and it's misbehaving and we say, what is it doing right now? And right now is like very recent history, say last 5 points of data. So in SQL, you do something like this. Not surprisingly, there's like a similar window function, right? I'm basically taking the row number in these partitions, and then I'm taking everything at the end. You can see there's the where rn is less than or equal to 5. So it's the last 5 points ordered by this row number. Again, in terms of like a emitted query from some code, like a web console, not that bad. But if you're talking about interactive usage, this gets pretty tricky. You've got to remember to sort things in the right way by the timestamp. And it seems to us easy to get wrong, right? Again, especially for folks who are, want to be able to do a pretty quick debugging process, but aren't necessarily SQL ninjas. Like it's tricky to be able to write, a kilobyte of text or something in order to ask fairly simple questions like, what is the behavior of the last 5 samples? Okay, so another really common thing, this comes out, we were talking about this earlier too, of dtrace. So dtrace makes sort of first class this idea of a quantization or a histogram. If you, again, in a debugging context, walk up to a system and it's misbehaving, you often want to just say, what is it doing, over the last day or hour or whatever it is. Just give me a quick summary of the data. And especially in a way that makes outliers very clear. And histograms are a really compact and useful way of doing that. So as an example, I mentioned at the beginning that we track API request latencies, and we do that in a histogram where we break out lots of things, but on the bins is basically the time. And then we count the number of times the API request was served within that time bin, right? So if everything is in like the milliseconds to seconds, we're fine. But if there's any sample in like 150 seconds or 1,000 seconds, like we're having a bad day, something is wrong, I need to go look and figure out what's going on there, right? So it gives us this really compact way of just saying, is the system behaving normally, or is it, are there extreme outliers in some form or another? Looking at the distribution is really valuable. So I actually didn't know how you would do this in SQL. You guys probably might know, but I did what any self-respecting engineer does these days, which is ask ChatGPT to tell me how you would emit a query. And this is what it told me. There are some weird things in here, which I'll get into in a minute, but the big pit, so there's this CTE at the beginning, which is basically the same as what we've seen before. The big case when statement is the relevant bit. So what we're doing here is basically taking this difference. We've computed the adjacent differences because, again, our histograms are cumulative, right? So we've computed the adjacent differences, and then I'm bucketing it into these different buckets with this big case when statement. So you could do this with a function. The ChatGPT didn't really realize that you could do this, but the main reason I think is that in the general case, you need a case when thing anyway, because if the buckets are not a simple function of the inputs, then you probably are going to have, these buckets are not all the same size, for example, and they're not all like equal powers of 2, for example. So in general, you would need something like this to do that, right? The weird part is that ChatGPT thought it was best to emit a text label, which is the point at the very bottom. If you can read it, it says this, there's this cast substring construction thing, which is basically pulling back out the first integer of the text label. And the reason for that is if you just do order by on a text string, it's going to be alphabetical. I don't want that. I want it to be numeric based on the left edge of the bin, right? So it's kind of undoing this inefficiency. We probably could have just emitted the left edge of the bin in the case when statement. But anyway, this is what you would do if you wanted a histogram SQL in general in SQL. And I mean, this is like a non-starter for us, right? I mean, there's no way I'm going to write this. Like, imagine you did this and you said, oh, I screwed up the buckets. Let me go and like find the right bucket and, which arm of the case when statement, and then correct both sides so you don't like miss something or overlap things or whatever, right? Very, very tricky, I would say. And we're definitely like starting to strain the familiarity points in the favor of something like SQL, right? So if we go back to our list, familiarity is like, we're kind of losing a little bit of that, right? Like we're in some fairly dark corners of SQL for people who are not, experienced database users. I mean, again, I think for most people here, there's nothing like revolutionary about the queries that we've done, but for some random Oxide engineer or for some Oxide customer, these things telling them like, oh, you want a histogram? Cool, run this like 4 kilobyte query is like, that's not really going to work. Is it possible? Yes. But I don't think most folks who run the queries would want to be able to write that manually very often. Okay, so you might say, well, the problem is with that previous query that we have this big case when statement, right? This huge chunk in the middle. This is the same query from the previous slide. So that's very verbosely expressed. We could probably express that much more succinctly, at least for certain common cases, right? So let's say my problem with this is that I want to be able to express that bucketization thing as a function, right? And so a hypothetical, totally made up function might look something like this. So this is the same query, except I've replaced the giant case when with this quantize function in the middle. Again, a made up name, but I'm just giving it, let's say it by default puts things into power of 2 buckets for whatever reason, right? Maybe it has an overload where you can give it the bin edges, but the default one is just look at the type and span the range with power of 2 buckets. So this would be much better in my opinion, right? Like it's a lot easier to understand. It's a lot easier to write. Most people would probably know what we're doing, even without a lot of documentation. But I've sort of stuffed a lot of the secret sauce into this function, quantize, right? And it's something that we made up that's not part of the standard. And so I have to write it again, right? I have to implement it myself. I have to document it. I have to, tell everybody, provide examples. ChatGPT isn't going to generate this for you, right? So it doesn't exist anywhere outside of Oxide systems if we were to use something like this.
why not do a view?
I'm not sure. Can you say more?
It's like a virtual table. You define that you call create view in a select statement,
Mhm.
and basically it's like a macro that gets inserted.
Yeah, so I know views are I see what you're saying. You're saying create a view which is does all of that histogram bucketization. So we write that giant query once and then we can
Yes.
query the view. I think that would work, yes, if you were interested in fixed buckets, which you often are. If you wanted to generate a histogram, right? Because the view would have the buckets in it, right? If I'm understanding correctly.
Correct. Yes.
Yeah, so you'd have this giant case when statement. So you might have a view per like bucketization or something. So I think that's an interesting thing. We had not considered that. I think it would definitely make if you knew a priori what those buckets were for the things that you cared about, I think that would be a useful way to do it. Yeah, I hadn't thought about that.
The other way, piggybacking on Andy's question, is often people define stored procedures if their application is just 20 different patterns or some small number of patterns. It becomes unwieldy if it's a lot more.
Yeah.
And then you parameterize whatever you need in there, which might be the number of buckets or the way you are doing imputation, stuff like that. Would that work, or you have a lot more than 20 patterns that or templates that people end up using?
Yeah, it's another good question. The short answer is I don't know. I think you could get away with a lot of that. I think we tried doing some stored procedures for some of the simple stuff initially. We basically didn't know enough about the kinds of questions that we wanted to ask to build on top of that. But it definitely is something. I think it can like the stored or like the like the view. I think you can get away with a lot of those things, right? I would say that the point that I want to make about this, I think still applies to both of those, which is that if you do this, it's really less SQL and it's select from where with some special sauce, right? Like you're selecting from the special view, which I have to tell people about, which is fine, or from a stored procedure, which again I have to document and implement, which is also fine, but it's sort of less. We're really only using like the select stuff and then, running some function that we've built, that we've documented, that we've implemented ourselves under the hood. So I think you can definitely do that. There's a lot of benefit to doing things like that. For our case, because we couldn't define a priori, say the buckets that people were interested in a lot of cases, it didn't work. I think, there are upsides and downsides is basically my point for that. Okay, so if we go back to our list of reasons to choose SQL, we've already lost a little bit of the familiarity stuff. We're losing again. The more we stuff things into this, like the quantize function or these stored procedures or other things that we need to implement and explain to people, we lose some of these other things like the documentation and the examples. And we're losing a little bit of some of the tooling stuff, right? Because now if everything is like a stored procedure or something, I may not be, if I'm implementing the actual query engine under the hood, the off-the-shelf optimizer or query planner, for example, may not know anything about may not know what to do with that. And so it may generate, who knows how well it's going to work in terms of generating a query plan for me, right? They're not totally gone. I can still use them probably in a lot of cases, but they're kind of, they're on tenuous ground, I would say. So what happens if we say, well, a lot of the problem is the data model, right? As we were talking about a minute ago, my tuples are not independent, right? There is an implicit or an explicit ordering to these, right? In terms of time, which I think is really inherent in the type of data that we're storing. And they're not independent in that later samples in a cumulative metric include data from before, right? So what if we say, I'm not going to store the data this way. I'm not going to model the data this way in our language, but instead I'm going to model it something like this with arrays, right? And I think there's a lot of benefits to this. So all I've done here is collapsed the rows that have the same metadata columns in red, and turned them into arrays in the timestamp in the vCPU usage column. So this is actually how I intuitively think of the data. There's some array of timestamps and values, and I've got some metadata, some key value pairs that's associated with it. This has the added benefit of deduplicating the red rows a lot, right? Which, as Andy mentioned, we're using ClickHouse to store the data under the hood. Even in that case where it's a columnar database and you've got really good compression algorithms, you're still going to get a huge performance benefit, a huge efficiency benefit by storing the data this way, because when ClickHouse has to run a query on the whole table, if you store it the other way, you are going to, or your ClickHouse will have to, blow all of that back up when it actually runs the query. So you've got CPU time to duplicate things, you've got memory, you've got to send that over the wire. So there's lots of problems with doing it that way. You still get the efficiency benefits of this. But the obvious problem that I'm sure everybody is pointing out is like arrays are kind of tricky in SQL, right? Like there's not a lot of support built into native SQL. It has like a handful of array functions.
Furthermore, like how big are your time? These arrays are going to be massive, right? Because you're
collecting. Yeah, exactly. That's another big problem, right? So if you really store it this way, we have, for some of these, we can have millions of data points, right? And like you quickly run into the limits of storing, in one page, or it's obviously not going to fit a page, but in one piece of data, one cell, storing these large arrays. Also, this actually isn't quite what I naturally think of the data. I actually, ignoring, ergonomics, the way I would sort of represent it is actually an array of tuples of timestamp and value, which is even shittier. So like, you've got really, it's a very sort of hairy set of functions that you're going to need for dealing with that, right? SQL's array support is pretty minimal. So we're sort of stuffing more into the kind of the secret sauce and like array functions, like some array filter function or something like that, right? So again, we have to implement that ourselves. We lose a lot of the documentation. We kind of get, we're sort of making more strikes against some of these. So it's really like SQL, please, like I really want you to work, but it's like kind of being pretty hard for us, right, to make this work. So we've really lost some of that flexible data model stuff where you can't really model it exactly how you want. You maybe are constrained. And then again, these kind of off-the-shelf tooling, things like the parsers or planners, are really sort of not so helpful to me anymore. So, we're kind of like, I guess we're stuck with death at this point.
Sorry, super quickly. Earlier with the array example, were those values cumulative values or point-in-time values?
Those are cumulative.
Cumulative.
I'm going to talk about that in a second, but those are cumulative.
All right, cool.
Yes. At this point, we have basically spent a while using this SQL prototype, trying to make something work for us. And we basically said, okay, we've written down all of these problems, all of these situations where it didn't quite work for us, where we had these questions and we found ourselves fighting the language. How can we do something different? So this is when we turned to the idea of our own query language of just, I want to start over. Let's talk about the things that we want from first principles that will do what we want to do and make our lives a little easier. So the kinds of things that we want, I want a concise and expressive syntax. So like that histogram thing, I don't want to write giant case when statements. I want to be able to sort of express these things pretty simply, pretty straightforwardly. I want things like that adjacent difference thing. I need that to be sort of first class, right? Or sort of done, as easily as possible, because we do that all the time. Things like, dealing with durations or intervals or whatever, we want that to be sort of very first class as well. So key analysis methods that we care about for time series. We want it to be suited to our data model, which again, we actually represent the data intuitively as a bunch of key value pairs and an array of time-stamped values. And that's how we return the data in the query. When you run a query, you don't get back a table, you get back key value pairs and an array, right? And like, we want to be able to operate on that pretty naturally. Obviously, our product has specific things that we want to be able to make easily available, things like that vCPU usage graphic, and then all the debugging stuff. We have a heavy debugging culture. So being able to do that easily, walk up to a system and quickly write these pretty simple queries in text that expand to something complicated or express a complicated idea, but that's very useful for debugging. That is definitely something that we want to make first class too. Also, as everybody here knows, writing your own query language is very tricky. There are tons of pitfalls and problems with doing that. So I want a query structure that's pretty flexible, something that I can build exactly what I need now and hopefully know more, and then add on to pretty easily as I need, right? As we decide, oh, hey, there are things that we need that we don't have yet, new language features, I want to implement those pretty easily. And also it has to be something that I can optimize pretty easily. I am not a database engineer. And so something where I can go sort of look at, what are the first 3 to 5 optimization tricks that any database engine implements. And I need to be able to do those for our query language as well, right? So again, this is our data model here that we kind of work with. And I like this idea from the Zen of Python. It's sort of the tenets of the Python programming language. And one of them is, easy stuff should be easy and hard stuff should be possible, right? And so I really want to make that easy stuff that we do, often I want to make that very, very easy. So obviously, the table stakes for this is being able to put go get data from this system, right? So in OxQL, that looks like this. It's this get table operation, and you're just going to get the data from that table. So this will return you everything. You obviously don't want that in almost any circumstance. So we need to be able to filter the data, right? So we pipe that to a filter table operation. So pipes are something that lots of the other talks in this seminar series have looked at as well. People have been interested in these for a long time. There's a lot of good reasons for liking them. They're very familiar, make it easy to parse the language, easy to optimize it. So we have this filter table operation for sub-selecting the data. And we have, different predicates you can express, things like equality and inequality. These things here on the right, the values, these are literals, but we support all of our different data types, obviously, that we care about, UUIDs and IP addresses and all that stuff. And you can do different kinds of operations like XOR and and OR and all that sort of stuff. Or it turns out to be like by far the trickiest thing to support, by the way. You were mentioning a minute ago, you were asking whether this data was
Cumulative.
Yeah, exactly. It was cumulative, or whether these were point-in-time values. And so that's part of the benefit of having a language like this. This get table operation can basically do that for us automatically. And the reason for that is that we maintain effectively a catalog of the data that we store, the tables that we store. We can look at the query and say, okay, somebody wants this vCPU usage data. I happen to know that's cumulative. So when I run this, when I actually execute this get table operation for them, I can automatically insert that delta in here for them, only for those cumulative data points, and I can return them that thing that they want. Obviously, that makes the query more complicated under the hood, right? The actual query that's being run is much more complicated. But the other benefit that I didn't quite talk about, but that's really valuable to this filtering based approach, this sort of pipeline approach, is that we can run as much as we need to in the database itself. We're using ClickHouse. So when I actually select data, I can try to push the predicates as far as possible towards the database to get the littlest amount of data from the database itself. But if there are things that I want to implement that are really tricky to express or very inefficient to express in ClickHouse, I can run those in our own query engine written in Rust, right? So as we develop new features, we've been able to add them quickly into the Rust-based engine. And then as we just learn how to either optimize them or express them more succinctly, or as ClickHouse SQL evolves, for example, we can take advantage of that and push some of that stuff into the database as well. So this flexibility in terms of the language being implemented in these pipes makes it very easy for us to optimize the pieces we care about, run as much as we can in the database, but then still gives us this escape hatch of running things in Rust as well as we need.
I think super quickly, I think the escape hatch is a great point, but I'm trying to understand right now if there is something in a view's computed columns that would not have been able to support this functionality. For example, with the deltas, you could use a computed column to compute that delta for you, I think
that's probably true. I think for us, it's a question of trade-offs. So one of the issues is that I didn't really get into this, but the efficiency thing is really important for us, I think more so than some other circumstances, because we are basically clawing all of the storage space and all the computing space back from the customer. We sell them the rack and we say, oh, by the way, you have n terabytes. Well, actually you have n terabytes minus 2 because we need so much storage space for all of our views, or if they're materialized, right? We need all of our storage space for views or these pre-computed columns, I think. So, it's still an open question for us of whether that's useful, whether that trade-off is worth it. But so far we have definitely said, look, we're going to try to store the data and then spend more time computing it and giving the customer as much of the storage space as we can. But it's a good question. Okay, let's see. kind of going back to the beginning, the first example that we used was this idea of averaging stuff over time, right? The vCPU usage, we want to graph 5-minute windows. So in OxQL, this becomes very easy to express. We pipe that to this alignment table operator that we have here. So this alignment operation is really just doing the same kind of thing that we saw in the SQL. It's basically rounding down to the nearest time interval, but we express it in a much more concise way. This alignment table operation takes this function mean within, which is one form of a reducer, but you can apply basically any function to it. So far, we really have just mean within. There's an interpolation method. But we take this reducer function and apply it to all of those groups, right? And then the other important point in yellow here is that we have first-class kind of duration windows. This comes out of, I mean, we're not the first people to do this. Like PromQL does this pretty well too, where they have this idea of compactly expressing intervals like 5 minutes here, but you could change this to 5 hours or whatever you want. This alignment method, the last point I want to make is that it's pretty important for time series data. If you want to do something like grouping within a single time series or joining across different time series, both of which OxQL supports, it's really important to be able to align our experience, to be able to align the data so that you are looking at things that occur at the same time window and you're not sort of dealing with this sort of misregistered data. So that's really valuable for us. I didn't quite mention it, but this get operation also sort of hides all of the complexity around histograms. So that delta thing that gets done for cumulative counters, scalars, it also gets done for histograms. And so we can express all of that in the same language without really having to change the query at all, which is kind of nice for us. And then the last example that I want to show is that idea of taking the last 5 data points. So for us, this is very easy. You just pipe it to this last operation, right? So kind of under the hood, we're doing exactly what you'd expect. There's some sort of SQL, limit by whatever operation going on under there. But it's very easy for somebody who's, walking up to a system and just running this analysis to be able to sort of add that. They say, oh, there was too much data. I actually just want the last point or whatever. So it's very easy to do that as well. So that's really kind of the bulk of what I wanted to get across today. I think the idea that I hope I've communicated pretty well is that if you are faced with this choice of SQL, I do think you should start with SQL, right? I mean, like, yes, SQL makes a ton of sense, right? There's a reason it's the lingua franca for data analysis. It's so useful, has all of these really great points, but there may come a point when you can't make it work for yourself, right? And I think it's important to always favor those boring technologies, the battle-tested technologies. And then this is the point that took me a long time to get to personally, was writing down the reasons that it didn't work. So like these examples that I've walked through, what would happen for me is I had this SQL prototype. And before that, we had another query prototype where I would try to make it work. And I would feel myself sort of fighting against the language for a long time. And then I would just sort of move on and forget about it and not write anything down, right? I think one of the things that I should have taken from my academic training is writing a paper, keeping a lab notebook, something like that should have been more of my training or more of, what I tried to do here. But I think even for that, it was difficult to tell other people what the problem in my company, what the problems were going to be when they started to use things. They would hit the same things themselves. And I think the real point about doing that is that you can effectively just say, okay, we've made this decision. Let's move on to something else with confidence. Let's just try we don't need to relitigate like the why SQL thing over and over again, right? We've written it down. If we want to revisit it, we can go back and refer to it. So for myself, I found myself obviously second guessing what I was doing all the time. And so being able to go back and say like, oh no, actually this is, this particular thing was extremely painful for us. And I think having that stuff written down is really, really valuable. So again, just for us, like the fact that it didn't quite fit our data model because, for example, histograms, arrays were tricky in SQL, right? The fact that we have these cumulative data made things very tricky. So it didn't really work, I think, in a lot of the kinds of data that we stored that we really heavily relied on, especially for debugging, which early on in the product was really valuable. OxQL, because we control it, it implements exactly what we need. It has this expressive kind of pipe-based interface that other people, we're not the first people to come up with this. Many people have thought about this, and it has a lot of attractive points. And again, because I implement it, having the query engine under our control, having the language under our control, being able to implement only what we need, I think was really a valuable thing. So with that, I just want to say thank you again for everybody. I really appreciate the opportunity to talk to you guys about what we did, and I'd love to take any questions.
I will applaud on behalf of everyone.
Well, thank you.
And open up to the floor for questions.
Yeah, I think this is a great talk. You make a very compelling observation that SQL is not really good at doing imputation and naturally doing a lot of this type of time series analysis. Um, I was wondering if, as you were developing this language, you had looked at others who have had this pain point. I think they've solved it in different ways. I think the imputation part was interesting. Like Influx has this Influx QL that sits above their scripting language of Flux. And I was wondering if you had looked at that, and if you had looked at it, like what were the big things that were missing, or things over there that you could learn from as you build this language?
Yeah, it's a great question. So I definitely looked at Influx. We actually evaluated Influx when we did our first selection of ClickHouse as the time series database. And so I had a pretty good background with their query language. I think in my experience, so I looked at Influx, I think, obviously PromQL is sort of in this domain is kind of the lingua franca. There's a lot of great things about that as well. For that one specifically, I think actually the major problem was that at the time, at least, I think it's now experimental, but at the time, histograms were not really well supported. And so it was very tricky to express a lot of the things we needed with histograms. So as far as like taking inspiration from them or you looking at things that they've done, I think a good example is, again, with PromQL, some expressive way of saying the filtering conditions that you want. PromQL has this nice syntax where you have these braces and you kind of have these tags. I think Influx has a very similar model. The idea of storing the data as like some metadata, some tags, or we call them fields, key value pairs, basically, right? And then you have some long list of data, arbitrary length associated with that, I think is really valuable. We found that, something like PromQL is probably the most agnostic language. Besides the problem with the histograms, we found it a little bit tricky to kind of map that onto the way we were storing the data. And I think with these kinds of languages, it's very often the case that, the underlying storage method for the data really does kind of leak a little bit into the language itself. So for us, like these, I talked a lot about the data model being these key value pairs and the arrays. The way we're actually storing the data is not arrays, but it's a separate table of fields and a separate table of the timestamps. And so we're using the full column. We're storing a value per column, right? But it really is this sort of thing that if you wanted to construct it into a table, you would join them and you'd end up with this massive table thing, right? So I think that taking another language like the Influx language or something like that, I think we struggled with a way to sort of get away from their existing data model is basically the problem. But I would love to see a way of either developing something like PromQL or whatever it is into a more, agnostic kind of time series specific language.
Thank you. That is a great answer, especially with the data model assumptions.
Yeah, thank you.
All right, question from Nick. You want to mute yourself, or do we need me to read it? Well, he asks, can you talk more about the lineage from Google Monarch and how it differs, is similar besides the data model mentioned in one of the RFCs?
Yeah, so we heavily base this on Monarch. So Monarch is Google's, the paper is called Monarch, like a planet scale time series database or something like this. It's a really good paper. We heavily based it on this, I think, because we had a couple of people at the time who had come from Google and they had experience with what was before that, this sort of Borg and Borg-Mon, data center analysis monitoring tool. And they had run into a couple of pain points around things like scalability. I think what we really took from Monarch was the data model. We did not take a lot from that paper in terms of the data organization. They had this very complicated, query direction sort of front end for sort of just taking their query, breaking it apart, querying different pieces of the data. Because their data is so big, it has to be sharded. So they spend a lot of time kind of figuring out, where do I go run the data, run some subset of the query on the data that happens to exist in one of the shards. And we're just, like most people, we're not at that scale. So we don't really have to take anything about that. The thing that we did really like was they have also histograms. We haven't done a ton with this, but one thing I really liked from Monarch is they have this idea of an exemplar. So in their paper, they show, I can't even remember what the actual time series is. I think it's something like API latencies, but they show this idea that you can show a graph and then you can point at particular things that look like outliers in one form or another. And so being able to tag things with exemplars, I still really want to implement this. We haven't done it yet, but I think that's a really cool idea that is probably very useful. The histogram summaries actually turn out to give you a lot of that, because usually what you care about are outliers, which are pretty obvious in a histogram. Yeah, I hope that answers the question, at least a little bit.
Awesome. All right. Any other questions? So my question would be, seems like the path you went down has to do with the fact that you have these accumulators, right? Normally in stream processing, every event is independent, but you're trying to backfill missing data because you have these. You're basically maintaining like a moving count, and then if you recognize you're missing data, you then basically inject the data back by taking the difference. How much does that problem go away if there's, it could be stateless, but like I'm not saying to bring in Kafka, because that's a large beast. Like just something that said, okay, well, I didn't get a timestamp within some range. Therefore, the next thing I know, I can subtract somehow or something like that. How much does the problem go away if you do that?
Yeah, that's a good question. So if I understand correctly, you're saying let's maintain some amount of state somewhere else that tells me, like, keeps track of that, either does the differencing for me automatically or something like that, right?
Yes.
So this came up a lot in our original design discussions, where we were concerned about who's responsible for getting the data. Are we going to have our program that actually collects it, which is called Oximeter, that's where the whole name for the language comes from. Is it going to pull the data, or is it going to get the data pushed to it? And both of these have trade-offs. The reason we ultimately landed with a pull model, Oximeter goes and fetches the data from the metric producers, the people who actually generate the data. And the reason for that is I think you need to do that anyway in a distributed system, because if you don't get data within a certain period of time, you're probably going to go try to check for it, which means you have to do pull anyway. So let's just make it pull based. It doesn't quite answer your question, which I think is important. I actually thought a lot about this when the way I'd actually thought about it was one could imagine inserting the differences into the data, into the database rather than the deltas. And I think you can definitely do that too. The problem is that if you want to look over some time range, you don't know the absolute value if all you're storing is differences, unless you go all the way back to the beginning. I know the deltas, but I don't know the absolute scale. Now you could store deltas and the scale. I also thought about that. Then it's sort of the pre-computed column idea, I think, that someone had mentioned earlier, that one had mentioned earlier. And that also is a great way to solve some of this problem. You're just doubling the size of that data, and we were concerned about the storage. So I think it would solve a lot of the problems, not all of them. But it could definitely get rid of a lot of these pain points if you do store the deltas. So I think if you're okay with certain other trade-offs being made, that would probably, it would save a lot of the difficulties that we've run into come around this accumulation.
And then my last question is, I had to step out for a second, so I might have missed this. Like you're basically doing a straight transpilation from your OxQL to SQL that runs on ClickHouse without any optimization passes or anything else?
No, we do some. So you might have missed this a little bit, but basically we take the whole query, we do some basic planning, and what that looks like. For example, we make sure that the fields you're referring to exist in the schema, stuff like that, that they're the right types, really basic stuff. And then we do a little bit of optimization. We basically push as much as we can. It's mostly predicates and limits into the database query itself. So we generate a query that does things like, well, the real details are that we take the query, we parse it, and then we split it into disjunctive normal form, and we take every disjunction, because you can run that as one consistent query in the database, right? We push as much as you can, all of the predicates ideally, into that database query. And then we get back, and if you want to do something special, like if it's a more complicated query, we can't prove that, for example, you can do the alignment in the database, then you would do that in Rust. But I think this escape hatch in Rust we've definitely used in some other situations. So the short answer is we do some optimization. It's fairly basic now. We have predicate push down and limit push down, and that's basically it.
All right, so one more question, and then what is your experience been with like the ClickHouse optimizer? Because it's sort of not as sophisticated as maybe, you know, some other systems like Snowflake and others.
Yeah.
Have you hit in queries where like, hey, this should run fast, and ClickHouse is just generating crappy query plans?
Yes. Yeah. So
you leave it at that.
Yeah. So I mean, I in a slightly more nuanced take, I think ClickHouse has been like phenomenal. It's an amazing technology. It works extremely well. It compresses data extremely well. I think the query optimizer is basically the kind of main thorn in our side. Luckily, the queries that we do run so far have been relatively straightforward, so we haven't had a bunch of problems with that. A lot of the problems have actually been around, and maybe this is not surprising. It will generate queries that just consume a ton of resources. And so you'll do things like just hit memory limitations, right? Or you'll do things where it's all of a sudden it's just spilling so much of the query to disk that it's like, oh God, it's going to take forever anyway. So like we have to kill it. It's a very resource hungry program, right? They spend a bunch of time writing really, really, really fast C++ that takes advantage of compression and vectorization, which is great for a lot of their use cases. And it becomes a problem, I think, in some other ones.
I have more questions. Sorry.
Yeah.
Last question. Like, so ClickHouse though is just running in another VM that the host can talk to, right? It's not like
it's actually running in an Illumos zone, which is closer to a container.
A jail.
It's a jail, exactly. Yeah, that's right.
Okay. Awesome.
Yeah.
Another quick question.
One more question. Is OxQL basically it as far as like the expressiveness goes? Do you need any more functionality that is not quite expressible yet, or do you think this is it?
Oh, no, I don't think this is it. Well, one example, we have not implemented like a rate function looking at, deltas, anything like that, which is very common. If you want to look like error rates, for example, you can't really do that in OxQL yet. PromQL has the rate function built in, which is quite nice. There's more things around like percentiles that we want to be able to do that we can't really do now. Percentiles are notoriously tricky for computational reasons, but there's a lot of sketches that you can use that are much more efficient to give you approximate answers. So that's definitely another one.
But so it sounds like fundamentally kind of your data model though is kind of stable, because I was reading the spec and you have things like subqueries. So the data model itself you think is more or less fine?
We think so.
All right. Cool. Yeah, so I'm just wondering if there's anything like out there.
No, I think we're pretty happy with the data model as a whole. It's worked pretty well. We get to take advantage of the compression that ClickHouse has when we store the actual time series, because those are all in one column, and especially for slowly changing data, it's very, very good at compressing all that. But then we don't duplicate things like those key value pairs, because we deduplicate them in the table that stores just that metadata as well. So I think we're pretty happy with the way that works, but there's a lot of other things in the language itself, functionality that like I mentioned, the rate stuff and other things that we want to implement.